Okay, Philippe told me yesterday that this was the worst talk slot because everybody is hungry, and now I cannot get it out of my head. So, I'm Shivani. I am going to walk you through a rule grouping performance pump tail. This is me. I am a developer at the OISF. I write C, Python, and Rust. I work on the development of mainstream SuriCata. It's helper tools, SuriCata Update, SuriCata Verify, and some internal tooling for the team. I like SuriCata, food, including some controversial choices, travel, math, reading about health, and fiction. Those two are not together. And these are my socials if you would like to connect. That's my picture from a vacation. As a part of my talk, I am going to cover a very brief overview of the detection engine and the pre-processing that is done by the detection engine. What signature grouping is, what is the importance and use of this thing to the detection engine, what impact does it have on actual network traffic matching, what is something called port grouping, which is a subset of the signature grouping, what was the issue that we saw with port grouping, which this talk is about, and an analysis of that issue and the results that we got, and how you as a user can see the signature groups that SuriCata creates. So from a very brief overview and very far overview, this is how detection engine would go. A packet comes to SuriCata. There is some pre-processing that happens to the packet. The packet goes to the detection engine where it is matched against some rules and indicators of compromise. Then the later processing happens as configured. So there is some setup that is done by detection engine, and all of this is happening before the detection engine starts. So before you see that message, engine started, these many threads running. First, we create an engine object, detection engine object, and we apply any configuration that is provided. Any matching structures that are needed later are initialized, and then we move on to rule processing. In a brief overview, this is what happens as a part of rule processing. We read rules from one or more files as you have configured. We put them all in a simple list, and then signature groups are created. Signature grouping happens in 4 stages. Firstly, we do some pre-processing and classification of signatures. Classification of signatures is actually something that was covered by Juliana in her talk yesterday. Then we go about grouping the signatures by protocol and ports. Then we group the signatures that are decoder events only. And then there is some final per group setup done. The highlighted things that you see on each of the slides are the parts that I am going to cover later on, and the rest of it is not covered in my talk. So internally, we use some properties to group signatures. There are some special grouping cases. So say for IP-only signatures, which means the signatures that only match on IP addresses, and the signatures that are matching on decoder events, they are special cases, so they are grouped separately. And then there is regular grouping, which is done for most of the signatures that we see. This is done by direction, by the IP protocols in use, and the ports. Ports is what, the regular grouping by ports is what we are going to talk about moving forward. So if you were to see how all of this is organized internally, you get some signatures, You see if the signature is TCP or UDP, what's the direction, and what's the port, and that's how we end up creating 4 different lists in the end for signature groups categorized by these things. So you would wonder how this is of use to detection engine. So this is how detection engine would be using signature grouping. A packet that comes in goes through the decoder. A flow lookup is performed against that packet. If that packet already has a flow, it'll use that flow signature group. Otherwise, it'll do a lookup based on the properties that I mentioned before. What is the IP proto? What is the direction? And what's the port? Now, why is signature grouping important? SuriCata can see, as many of you already talk about, very high network rates. So it's impossible for us to match against every packet, against every single signature that is provided. So for example, if you're seeing 1 million packets per second, time budget to do all the processing for that one packet is 1 microsecond. If you go about matching that packet against every single signature, it gets very costly. So SuriCata needs to be smart about dealing with high packet rates without losing precision, as it's very, very important. There are several things that SuriCata engine does as a part of work avoidance. So whenever there is high traffic rate, SuriCata is getting overloaded, or we know that in the future it will get overloaded. There are a bunch of things done. This is one of those things that SuriCata does before the engine even starts. So this will bring down the latency in detection, which would happen otherwise. I'll show you some stats later on, which give you a bit of an idea how much that latency could be if this was not happening. Okay, this is the next slide itself. So here we have 2 scenarios. One, the default signature grouping that SuriCata does, unless you have changed the settings somehow. I will show you what settings those are in suricata.yaml a bit later on. And how SuriCata would perform with a single group without prefilter. Prefiltering is an interesting topic, but it was not a part of my research, so I am not going to cover that. And it is not possible to switch signature grouping off in SuriCata. So this is the best way to measure what the impact of kind of without grouping would be. But there is still some optimization involved on the right side in signature group without prefilter. So you would see that in the default signature grouping state, the engine start time is high because SuriCata is taking all its time to be smart about grouping signatures and applying doing prefilter optimizations and figuring out a way to provide the signatures as precisely as possible and for the highest match performance. And with the single group without prefilter, the engine start time is low because SuriCata is trying to not do any of that, well, at least most of that. But the rule matching time for the default signature grouping is very, very low. I should have probably measured it in microseconds, but you can see that it's very, very low. But for a single group without prefilter, it's quite high. These tests were performed on ETBro rule set with a small pcap. So you can probably estimate that if you got actual traffic in here, how much of an impact it can have. Now coming to port grouping, what it is, as a part of the signature grouping process, we look at each rule and we see what all comes as a part of that rule. A rule could come with multiple port settings. So you could define ports as a single port in a rule, a list, or a range, or a combination of these. Signatures that use the same ports are put in the same group for precise matching. Now, based on a priority order among signatures and ports, the signature groups are sorted in the descending order by the number of signatures that use them. This is to be as precise as possible for the common port settings, as such rules would be evaluated a lot. Good thing is that you can actually configure these priority settings. These are the settings in SuriCata.yaml that you have to change if you want. By default, we actually pick the most common ports which see the most traffic. These are TCP priority ports, and these are the UDP ones, and you can configure them if you want it. Now, coming to the issue with port grouping. We were reported by AWS that a particular rule set took an excessive time to load, and by loading we mean that the entire startup time of the engine was quite high. When I say quite high, I mean it took 9 minutes 45 seconds on my system to load. So that's how much it took for the engine to get started. The interesting thing and the different thing about this particular rule set was that it consisted of different port combinations. So these were our observations. It took really high time to load, and upon observing the flame graph of this particular rule set, there was a high stack trace of a particular function, which was making some recursive calls internally. This function was about a certain part of the port grouping process. There were also several TLS rules that were part of this rule set that stood out to us. Upon doing a preliminary analysis, although, we broke the rules down and categorized them differently to isolate the problem. They were broken by port category, by protocols, because there were too many TLS rules. We wanted to make sure it was not about TLS. There was some mix of protocols and some mix of port categories. It was concluded that the issue was happening when there was a combination of many explicit ports and port ranges, and it had nothing to do with the protocol. Another thing that we observed was that the algorithm for port grouping was complex. So that recursive function that we saw was with a particular high stack trace was actually trying to resolve the overlaps among ports, which is something that SuriCata does internally to build signature groups as precise as possible. And all of this logic was complicated, and it used some dynamic data structures. So we were constantly changing some data structures and actually then querying them, looking through them if something was updated. All of this was in a quest to build a simplified list of ports or port ranges which did not have any overlaps. Breaking down the problem very simply, it could be defined as a combination of 3 problems. First was finding all the overlaps among the port ranges. Second was breaking down the ranges. And third was copying appropriate signatures to the designated ranges. So for an example port range list like this, we are assuming all of these port settings, port lists came from certain rules. The first problem was solved by actually just drawing it on a number line and seeing overlaps. It was easy to see that overlap resolution can be done maybe in a simpler way when we try to plot it like this. Is that visible? Yeah, okay. So maybe there existed a simple solution. The other problem was to break down the ranges. So for that, consider any range from a given port 1 to port 2 as a valid range, and use the method of elimination in the next step to make sure that we have only the correct ranges as a part of the final signature groups. The last problem was to copy appropriate signatures to the designated ranges. So any ranges that were considered valid, but while performing lookup did not have any signatures associated, they were eliminated from the final signature groups. So these were solutions, but they had problems. We had issues with boundary overlaps, invalid port ranges, and ultimately the search for overlaps with the existing signatures was a bit expensive because we were still storing them in a linked list, and we were walking through the entire linked list every time we wanted to check if there was an overlap with the existing signatures. So in order to solve the first problem of boundary overlap was a problem, by the way, as shown by this. For given port 0 to 3 and 13 to 70, we now had ranges 0 to 3, 3 to 13, and 13 to 70. You can see that 3 and 13 occurred twice, and all the ports in between, which shouldn't have been there. In order to fix this, we started to store more info corresponding to every port, like whether it's a single port or a right boundary. And if you can visualize with me, this is all happening on the number line. So whenever we find a boundary, we like push on the number line on both the sides, and we're like, I'm going to look after this point from here and before this point from here. Second problem was invalid port ranges. So for the same example, range 3 to 13 should be invalid, as I already said. So that was also solved by the same concept of storing more information corresponding to the ports. And then it was simpler when we created a range like 4 to 12, and it did not have any signatures because the first signature came with 0 to 3 and second came with 13 to 70. 4 to 12 did not match any signatures. We just eliminated that range. The third and the last problem was search for overlaps with the existing signatures. As I said, it was stored in a linked list still, so upon looking for a solution to this problem, I encountered upon interval tree, which is a special type of red-black tree that stores intervals in its node, as well as an extra variable that stores the maximum high in any interval of a subtree rooted at that node. So an example interval tree has been shown here. On top in every circle, it's a red-black tree, by the way, very perfectly balanced one, so maybe not very true, but for all cases. But in the upper part of every circle in there, we are showing the port ranges, and the lower part, it's the maximum of the right high boundary on that subtree rooted at that node. The cost of finding all possible overlaps in case of interval tree goes down from big O of n square in case both the things were same, or m into n if the number of ports from the signatures and port ranges differed, to a minimum of big O of n square and big O of k log n. Now, this new solution came with a bunch of pros for us. We found that we could always create the smallest possible port ranges at any given point. This is good for precision, which we wanted. And wherever we could merge the port ranges, we did so under the hood. At the most, we can have 65K port objects now, so we knew a bound, an upper bound on this. How many would we have internally? And there was a concrete upper bound on the time taken by this part of the code, which was now our most expensive operation, which was the lookup through the interval tree. These are some results in numbers. The base revision took 9 minutes 45 seconds to roll on my system, and the final benchmark was 29 seconds. This was a 20x perf upgrade. The algorithm that I walked you through, the changes in algorithm that I walked you through, actually contributed to bringing it down to 1 minute 10-ish seconds, and some more work was done by Victor, which changed sorting algorithm from maybe insertion sort, I don't recall exactly which one was it, to the C libraries qsort and some SIMD optimizations, which brought it down from 1 minute 11-ish seconds to 29 seconds, finally. I wrote a blog post about this a couple of months ago, which you can read if you want to get more information on the before and after and how SuriCata's internals were. I was hoping to cover more in this talk, but due to time constraints, I have brought out the important parts only. This performance change is available in 706, starting 706, and in all the following versions, and of course in master. So this is how you can see signature groups on your own if you wanted to see what SuriCata is doing with the signatures that you're providing it. You will have to make some changes maybe to suricata.yaml to get these output files and run with the engine analysis, which is a very important and nice feature of SuriCata, to see how SuriCata engine is analyzing all the rules. And you have to check the rule group.json file. Then you would see in the output something like this, a couple of things. You can see there's something called rule group over here. I don't know if you can see my cursor. Okay, yeah. There's something called rule group over here, which has an ID, which tells which rules are a part of it, which ports are a part of it, which protocol it is, which direction it is, a bunch of other things that SuriCata does as a part of the grouping. It analyzes NPM stuff and other things, which it also ends in here. Oh, there's something called score. That's what defines the priority among these rules. Highest score is given to the TCP and UDP priority ports that you define in your suricata.yaml. There are some other criteria internally that we sort them by further, like NPM, negated NPM, and some others. So you can see a number like that. So you would see, yeah, this is how the rule groups would look like if you wanted to check. And that's it. Special thanks to AWS for bringing us an opportunity to improve and the thorough testing of SuriCata. And my mentor, Victor, I thought it would be easy to spot him with these glasses, but I realized everyone is wearing these glasses in my team now. So I thought I'll specify for all the support and doing the last round of the upgrades. Thank you. Questions?
Hello. Thanks, Shivani, for the talk. I don't have a question, more of a comment. When we first saw the blog at ET, we really appreciated the content that you shared relating how to improve our own understanding of how to write efficient rules. So if there's any more opportunities to further create blogs or review how to expose better signature performances for rule writers, we would really appreciate it. So love this talk. Hope to see more. Thank you.
Thank you very much. Yeah, the priority ports are one things that you could probably look at. There are more settings. Probably the detect group in suricata.yaml is interesting to check out for you. I have not looked at everything in there, so I won't be able to guide on anything in particular other than this. But yeah. Hungry people knew it. No questions? Okay.
One other question. At some point you showed that you could do a port grouping or other options. Could flow bits be part of one of these options that could be added?
That could be added where?
To role grouping, use flow bits to do role grouping.
I don't know. This grouping is, I think we are not really doing it on options as far as I understand, right? We are only doing it on the proto direction and ports to have a precise thing, like if
There were app layer events on your slide, so.
Oh yeah, that's like the app layer event. What was that keyword? Oh, sorry, yeah, decoder event. That's the decoder event. That's because the decoder events are for the kind of packets that still haven't found out, like even if they are IP, so they're far from understanding where they are, whether they are TCP or UDP. So that's why we group them separately, because we don't know anything about them. What? Yeah, broken packets, right.